Assalamu alaikum, my dear students. Welcome to your chemistry second paper class of standard 11. Hope all of you are fine, safe and sound. Today I will discuss mainly Dalton's law of partial pressure. John Dalton, an English chemist, he found that in the absence of chemical reaction, the pressure of a gas mixture is the sum of the individual pressures of each gas alone. That means if we measure the pressure of gas mixture of more gases, then we will see the total pressure will be the pressure of each individual gas. So, if we consider three gases, gas A, gas B and gas C, and if the pressure of gas A is PA, gas B is PB and gas C is PC, then we can say the total pressure of the mixture of these three gases, gas A, gas B, gas C, will be the sum of their pressure, PA, PB and PC. So, the total pressure of gas mixture is actually the sum of pressure of the individual components of that mixture. So, we can write the Dalton's law of partial pressure like this way. The total pressure of a mixture of non-reacting gases in a system is the sum of their partial pressure. So, what is partial pressure? Partial pressure actually the pressure of individual gases of a mixture. And we can write the definition of partial pressure like this way. The pressure that would be exerted if it were present alone and occupied the same volume as in the mixture. That means if the component gas is kept alone in a container, then it will apply a specific pressure. Then if with the mixture when kept in another container, then it will apply the same pressure. So, partial pressure actually the pressure of component gas of a mixture. If a container with a volume V having three types of gases X, Y and Z will exert partial pressure of Px, Py and Pz on the wall. Now, I will discuss about the mathematical explanation of Dalton's law. That means how can we derive Dalton's law mathematically? Now we will see. Let's say, let us consider then N1, N2 and N3 moles of three non-reacting gases are kept separately in a container of volume V. That means their volume is fixed and their amount, that is mole, is different for three gases. Now, if their pressures are P1, P2 and P3, so it will be actually their partial pressure. Now, if these non-reacting three gases are mixed in the same container at same temperature, then the mixture of gas exerts a pressure, that is total pressure of that mixture will be Pm. Now, according to ideal gas equation, we can write, we know that PV equal to nRT, this is the actually ideal gas equation. So, for sample 1, we can write P1 equal to N1 RT divided by V, because here RT and V, these three are constant for sample 1 gas. Now, for sample 2, P2 will be is equal to N2 RT divided by V and P3 is equal to N3 RT divided by V. Now, if we add these three pressures, we get P1, P2, P1 plus P2 plus P3 equal to if we take common RT by V, then we will get in bracket N1 N2 plus N3, and we know that N1 N2 and N3 actually the mole of component gases, and their addition actually total mole of gas mixture. So we can write P1 P2 P3 equal to nRT divided by V. Now if the pressure of gas mixture, total pressure of gas mixture is Pm, then according to ideal gas equation again we can write Pm equal to nRT divided by V. So now if we add these two equations, then we will get Pm equal to P1 plus P2 plus P3, and this is the mathematical derivation of Dalton's law of partial pressure. Here you can see the total pressure of the mixture is equal to the addition result of their partial pressure of each component gases. Now this partial pressure of component gas is actually closely related with the mole fraction. Now we will see how the partial pressure and mole fraction is related. Follow this. If we consider a mixture of non-reacting gases A, B and C, the partial pressure exerted by each gas can be calculated by ideal gas equation P equal to nRT like this way. You have seen in previous slide. Then where Na, Nb and Nc are number of moles of gases A, B and C respectively. Now by Dalton's law of partial pressure we know that total pressure equal to the summation of partial pressure. So putting the value of partial pressures we will get this equation. Now here partial pressure Pa is divided by total pressure equal to, putting the value of partial pressure this here, this, and divided by putting the value of total pressure. So like this way we will get partial pressure is divided by total pressure into mole fraction. Mole fraction is actually the mole of a specific component of a gas mixture divided by the total mole. This is actually the mole fraction of that component gas, and it is denoted by capital X. So here XA, that means mole fraction of A gas equal to mole of A divided by total mole of all gases. So here partial pressure of A gas equal to mole fraction of A gas into total pressure of that gas mixture. So like this way mole fraction of component gases and partial pressure is closely related. Now we will see the application of Dalton's law. Application of Dalton's law, that means in where we can implement this law. At first, collection of gases over water. That means you know that we have to collect the produced gas in different ways. It actually depends on the produced gas which are lighter or heavier than air and water. Here we will see our produced gas is oxygen gas, and this is light than that of air and water. So for this we have to collect this gas in a specific way, and here this method is called downward displacement of water. So when a gas is collected over water, provided that the gas is insoluble in water, so gas becomes moist. So the total pressure of moist gas will be what? According to Dalton's law, we know that total pressure equal to individual pressures of component gas. So here two types pressures we obtained: pressure of dry gas plus water vapor. That means pressure of water vapor. So if we want to determine the pressure of dry gas, then we have to subtract water vapor pressure from total pressure. So like this way we can measure the pressure of dry gas from this method. And this is one application of Dalton's law. Now another application is determination of pressure of a mixture of gases kept in separate vessels. That means when different gases are kept in different vessels, and if we consider them to mix with one another, then how can we determine the pressure of the mixture of different gases? It will easily determined applying the Dalton's law of partial pressure. Let's see. At constant temperature, a gas is kept in vessel 1 whose capacity, that means volume, is V1 at pressure P1, and B gas is kept in vessel B of capacity V2 and at pressure P2. That means A gas and B gas, they are kept in different vessels of V1 and V2 volume and whose pressure is respectively P1 and P2. When they are actually separated by a stopcock, if we open the stopcock, then what will happen? This A gas and B gas mixed with each other. So when they mixed thoroughly, then we will determine the pressure of that gas mixture of A and B. So here temperature is constant. So according to Boyle's law, we can write P1 V1 equal to P2 V2. So here P1 we can consider P1 V1. That means in case of A gas, we will write P1 V1 equal to P2 V2. That means partial pressure into total volume. After mixing, their volume will be V1 plus V2 because they are separated. But here when we will open the stopcock, then they will mix with each other. So their volume, actually total volume, will be the volume of two vessels. So here partial pressure of A gas into total volume equal to P1 V1. That means total pressure and volume, first pressure and first volume. So here partial pressure of A gas will be the P1 V1 divided by total volume. First pressure, first volume. First pressure means pressure of A gas equal to pressure volume of first cylinder, first vessel divided by total volume. So that pressure which we will get will be the partial pressure of A gas. Now in case of second gas, also partial pressure of second gas will be the pressure of B gas, specific pressure of B gas and specific volume of vessel 2 divided by total volume, V1 plus V2. Now from Dalton's law of partial pressure, we know that total pressure of the gas mixture will be the partial pressure addition result of partial pressure. So now putting the value, we will get this. So the equation will be Pm equal to P1 into V1 plus P2 into V2 divided by V1 plus V2. So using this equation, actually we will solve different problems based on Dalton's law of partial pressure. Let's see problems based on Dalton's law. Follow here. At 17 degrees centigrade temperature and 770 millimeter of mercury pressure, 600 milliliter oxygen gas is collected over water. Calculate mass and volume of oxygen gas at STP. Here is given 17 degrees centigrade temperature, vapor pressure of water is 14.5 millimeter of mercury. Actually, vapor pressure at the specific temperature is always given you to solve the problems. So it will not be a problem. So how can we solve the problem? Already you know that when we will determine the pressure of dry gas from the moist gas, then we will know the relation pressure of dry gas equal to total pressure minus vapor pressure. So here total pressure actually 770 millimeter of mercury pressure and there is given vapor pressure. So at first we have to determine the pressure of dry gas like this way. subtracting water vapor pressure from total pressure. Then what we have to determine? Mass and volume of oxygen gas at STP. So at standard temperature and pressure, we have to determine the volume of oxygen gas. Follow here, in your math there is given volume of oxygen gas, and also there is given temperature of oxygen gas, and also you determine the pressure of oxygen gas. So from the formula P1 V1 by T1 equal to P2 V2 by T2, from this equation you can easily determine the volume of oxygen gas at standard temperature and pressure. So here you have to determine the volume of oxygen gas at standard temperature pressure. So if you take this V2, so others values you have to put in V1, and standard temperature, that is 273 Kelvin, and pressure 1 atmosphere, since there is given in millimeter of mercury unit, so you have to take 760 millimeter of mercury unit. So like this way, at first you have to put the values of all factors, then you can easily determine the volume of oxygen gas at standard temperature and pressure, like this way. Now also you have to calculate the mass. How can you? Here easily you know that at standard temperature and pressure, we know that the volume of 1 mole of gas is same 22.4 liters. Since there is given volume in milliliters, so the mass of 22,400 milliliter oxygen gas is actually 32 gram. So 1 milliliter is how many, and the obtained volume is how many. Easily unitary method you can determine the mass of the produced oxygen gas. Now follow the another math. Ammonia gas is kept in 700 milliliter flask at 70 centimeter mercury pressure, and nitrogen gas is kept in another 500 milliliter flask at 80 centimeter mercury pressure. Two containers are connected with a stopcock at constant temperature. Calculate the total pressure. You know that. How can you calculate the total pressure? Total pressure is actually P1 V1 plus P2 V2 divided by V1 plus V2. So we can easily solve this problem here. If we consider P1 is for ammonia and P2 is for nitrogen gas, so putting the value correctly, we can easily determine the total pressure. Now follow the another math. At constant temperature and 30 centimeter of mercury pressure, 200 centimeter cube hydrogen gas at 40 centimeter mercury pressure, 300 centimeter cube nitrogen gas are stored up in 400 centimeter cube gas cylinder. What are the partial pressure of component gases and the total pressure of this gas mixture at that temperature? At first you have to observe carefully which are given and which you have to determine. Follow this. Here you have given pressure in centimeter unit, and volume is centimeter cube. Centimeter cube is actually 1 centimeter cube equal to 1 milliliter, so it will not be a problem. And follow here, two different gas, hydrogen and nitrogen, they are stored in different vessel, but in the next time they are mixed in another vessel of 400 centimeter cube volume. So here you have to divide it by not V1 plus V2. Here total volume will be 400 centimeter cube. It is very, very important in problem. You have to follow here. When the separate vessels are just connected through the opening stopcock, in that cases total volume will be vessel, they are different vessels. Here 200 and 300 centimeter cube. So in that cases its total volume should be 500 centimeter cube. But when the gases are mixed in another container of different volume, in that cases that volume of that vessel in which the gases are mixed, that volume is actually the total volume. So here our total volume will be 400 centimeter cube of gas mixture. Follow the solution. You know the formula P1 V1 plus P2 V2 divided by V1 V2, but here V1 V2 is not here. Actually total volume will be V, and that is 400 centimeter cube. So now easily you can calculate the total pressure, and now you know that total partial pressure is actually you can determine like this way. Partial pressure, since there is not given any amount, so you cannot use the mole fraction here. So in this case you have to determine the partial pressure like this way. P1 V1, that means pressure of hydrogen and volume of hydrogen gas, and V actually total volume. So with the compared with total volume after mixing, the partial pressure of hydrogen gas will be, we have to determine like this way. Now follow the another math. A mixture contains different amounts of hydrogen, nitrogen and ammonia gas. If the gas mixture is kept in a vessel of 10 liter volume and 90 degrees centigrade temperature, then what will be the total pressure of gas mixture and partial pressure of each component gas of gas mixture? So at first you have to determine the total pressure using the ideal gas equation, PV equal to nRT, where N, at first you have to actually determine the amount of different gases in mole, then you have to calculate the total mole. So that will be the N. So using PV equal to nRT formula, you will easily determine the total pressure. Then by using the mole fraction, here I have shown how can you calculate the mole fraction, you know that. So here using mole fraction you will determine the partial pressure of each component gas. There are hydrogen, nitrogen and ammonia. So my dear students, like this way you easily solve different problems based on Dalton's law of partial pressure. Also simply sometimes there is given total pressure, also partial pressure of all component gases except one, and in that case you have to just ask to determine that component gas, partial pressure of component gas. So in that case just simply you have to determine, you have to subtract the pressure of other component gases from the total pressure. Like this way this type of problems you can easily solve. I hope there will not be a problem to solve any problems based on Dalton's law of partial pressure, because all types of problems which can be possible from this Dalton's law of partial pressure already I have discussed. So please, you will practice at home more and more. There are a lot of problems in your book of different writers. So if you practice more, you will be more perfect, and you will be more skilled in calculation, and you can quickly solve all types of problems based on Dalton's law of partial pressure. So today after this I kept here some SW. I know you are now busy in giving different tests of different subjects, but please you will try to solve these problems and you will submit to me within 4 or 5 days, no problem, but please you will do these maths. I hope there will not be a problem. If you do these problems, then it will just increase your satisfaction or confirmation. So please do this and submit in my personal ID. Today after this, everybody keep yourself safe and sound. Goodbye.